Alright, in this video tutorial we're going to talk about one sample t-test. We're going to become familiar with the concept and the calculation using both formula and built-in functions in R, and finally interpretation of the one sample t-test. We use one sample t-test to determine whether or not the sample mean is statistically different from population mean, or in other words, whether this sample comes from a population with a specific mean or not. For example, you may want to see whether the average BMI of the randomly selected students in several universities across the United States is significantly different, which means less than or greater than or just different from the BMI of the national average. So we can test this with one sample t-test. Or another example, we know that the national birth weight of babies born in the US is 3,300 grams. We want to test whether for mothers who live in poverty, the birth weight of babies is significantly lower than national average or not. So that's another example of one sample t-test. Notice t-test can also be done between two independent or two related groups, which is the topic of the next videos. Before running the test, there are several assumptions that has to be met for the one sample t-test. First, observation has to be independent from each other. They shouldn't have any effect on each other. And also, the samples should be collected randomly. And finally, the distribution of samples should have an approximately normal distribution, or the sample size should be large enough. We can use this formula to calculate t-test. So in this formula, x bar is our sample mean. So if we have a bunch of observation, we calculate the mean of them. And mu is the population mean, which is for the entire, for example, entire US or entire state. And S is standard deviation of the sample. So when you have a sample, you can take a standard deviation of that. And N is sample size. So actually, t-test is difference between sample mean and population mean. But we also consider the standard deviation of sample and sample size in the calculation. So we use t-test when we have a small sample size, like less than 30 observation, or when population standard deviation is unknown, which is most of the time unknown. This t-statistics, or this computed t-statistics, is then compared with the critical t-value with n- degree of freedom for making decision. So let's see an example how this works. So here we have a data set of 20 observations of 20 individuals, and we have their IQ level. Okay, and the data were randomly sampled from a hypothetical population. For example, a hypothetical country with a population average of 95. We would like to know whether the average IQ, which is here, is 101. The average IQ in this sample is statistically higher than the or maybe different than the average IQ level in the population, which was 95. For this particular sample, it seems that it's greater than 95 or national average, but the question here is whether or not it's statistically significant. Could they have higher IQ just by chance? So statistically significant means we are confident that this is real and it's not by chance. And remember that in t-test, our sample was collected randomly and they are independent from each other. So in the R Studio environment, first of all, I make a comment that shows the purpose of this study: one sample t-test for IQ level. Okay. And the first step is to load the data set. which we use read.csv, and first of all we use file.choose to allow user to select the file, and then we have to set the header true. And before I run this test, I save this in an object with the name of data. Okay, and then click run, and so iq.csv. So you can see that we have 20 observations of 7 variables. So we can look at the data set, the few line of the data set. So check 10 lines of data. First lines of data using the head command, head of data, and then 10. So these are the first 10 line of the data. Okay, so IQ, so this is gender. 1 shows male and 2 shows female. So here you can also see that we have 1 equals to male and some of them are female, and we have IQ, we have volume, area, and other attributes. So what I'm gonna do is I'm going to extract IQ as an object to avoid using $sign a lot. So I extract IQ from this data set, IQ from data set. So from data, if I use $sign, then I select IQ and then I store it in an object with the name of IQ. So here is IQ, I can see the values for the IQ. Okay, so our null hypothesis is that there is no difference between your sample IQ mean and population IQ mean from a statistical viewpoint. So I create a command that hypothesis test. So our null hypothesis is no difference between sample mean and population mean, but alternative hypothesis is our sample mean is greater than population mean, which is 95. We want to test this hypothesis at 95% confidence level. The first step is to visualize the data using a box plot. So visualize the data using box plot command. Box plot command for IQ. I can create the, but let's make it a little bit nicer. For example, I can add a YLAB. I'm gonna add a label to the y-axis IQ, and also I can, instead of the vertical numbers, I can have horizontal number with the using the LAS command, and if I set this to 2, the numbers here will be horizontal. Okay, and also we have add the YLAB. We can also add the population mean to this graph. So using the AB line command, and then horizontal line with the value of 95, and also with the color of red, and line widths of, I don't know, 3. Okay, so this is population mean, and Remember that this value is median, is not mean. So mean of the data. So I can add the mean of the data to this plot. So using the AB line, right? So I can add the, what is the mean of IQ? So mean of IQ, I can add a horizontal line with the value of the mean of IQ and the color of blue, and the line widths of 3. Okay, so this is the sample mean, which was more than 100, right? And this black one is just a median, which divides the data, 50% of the data below, 50% of the data above it. And this one is the average or mean of the sample. So we want to see whether these two lines, the difference between the population mean and the sample mean, is statistically different or not, or if it's just by chance. We could also use, instead of these two line of code, we could use the C command to avoid typing this 2 times. But just for the sake of simplicity, I didn't make it more complex. I'm going to solve this problem using 2 methods, table method, or using the formula, and also the p-value technique. So let's start with the table technique. Okay, so method 1 table or formula. So if we look at the formula here, we have to measure the sample mean. We know the population mean, which is 95. We have to measure standard deviation of the sample, and then sample size, which is 20, I think. Yeah, 20. So we just plug in the values into this formula. We can measure the t-test. So we need mean of IQ minus the population, which was population mean was 95, and then I want to divide the entire numerator by standard deviation of the IQ and divide it by SQRT, square root of n, which was 20, right? And then I put everything in parentheses because I don't want to divide this number only by this number and then divide it by this value. So I put this into the parentheses, and the result will be the t-test, right? So I call this t1, and if I hit run, so the t value is 2.03. I can type it here. So that's TS statistics that I have, 2.03. So we need to compare this TS statistics with the critical value. So how can I compare it? What is the critical t value? I can't find it from, if I Google t table. Okay, so we're going to have, if you look at this value, we are doing the hypothesis test. It's a one-tailed test, right? So we have to look at the t table for the one-tailed test, and this one is this one is one-tailed test because it's just one shaded one side of the distribution. But if you look at the degree of freedom is n minus 1. We have n is 20 for us, right? So n minus 1 will be 19. And so if I look at degree of freedom, here is 19, and we are going to do this test at the 95% confidence interval, right? So significance level will be 1 minus 0.95, which is 0.05. So the intersection of these two gives us the critical value, which is 1.72. Okay, so critical value is 1.72. So our t-test is 2.03. Okay, so the interpretation will be, so our t-test or our test statistic or t-test, which was 2.03, is greater than the critical value. How could I find the critical value? Using the t-table, and it depends on the degree of freedom and confidence level, right? So we wanted to do this test at the 95% confidence level. So I looked at the t-table at 95% confidence level, degree of freedom of 19, it was 1.73, right? So this one is greater than critical value, right? 1.73. So which means that it falls into the critical region and it rejects the null hypothesis. So it rejects that there is no difference between sample mean and population mean. So we can accept that the sample mean is greater than 95. So the interpretation is, we can conclude that we have enough evidence that the individuals in this group have higher IQ level than the national average, and it is statistically significant. It's not by chance, okay? And at the 95% confidence level. So that's the interpretation of this t-test. So another way, which is much easier to run this t-test, is using the built-in R function. Okay, so method number 2 is actually is called p-value technique. So for the p-value technique, we use a test with the name of ttest, this command. And for the t-test, we have to put the vector name, which is IQ, as the first argument, and then we have to set these values, set these parameters. Okay, so let me just copy this and paste it here. So I want to do the t.test for the IQ, and so I just have one variable, one group, so I don't need the second one. So the alternative hypothesis is, for this case, is only greater than, right? So the alternative hypothesis is greater. So if it was a left-tailed, we should use less. If it was a two-sided test, we should use two-dot-sided. So I just type alternative equals to greater. Okay, I could also copy and paste it from the above, but so alternative is greater, and the mean was 95, right? So the population mean. So this is not a pair t-test, this is not a variance equal, this is not really important, but we want to do the test at the 95% confidence interval, right? Confidence level. So I paste it here, or I just next line. So I'm going to run the t-test on the IQ level to see whether it's different from the population mean, whether it's greater than the population mean at the 95% confidence level. So I select both of these lines and then click run. So you can see we get the same value for the T1, right? So that we use just a plugin, use the formula. So R automatically gives us these values, and also automatically R identified that this is one sample t-test. The t value is 2.03. The degree of freedom, which is n-1, we had 20 observation, which is 19, and the p value is 0.02, which is less than 0.05, like a critical value. So the results are statistically significant. They are not by chance. So we reject the null hypothesis at 95% confidence level. So and also it gives us the confidence interval that the population mean is between 95 and positive infinity, right? So that's the confidence interval that t.test automatically generated for us, compared to what we did using the formula, just plug in the values. So let me change the confidence level from 95% to 99% to see what will happen to the confidence interval, right? So confidence interval is from 95 IQ of 95 to infinity. If I use 99% confidence interval, and so 99% confidence level, sorry. So 99% confidence level. So what will happen to the confidence interval? So it was 90. It started, IQ started from 95 to infinity. Now it will start from 93. So to make sure that we are 99%, it increase the confidence interval, right?